Hello everybody and welcome to our lesson on section 15a, which is about simple rules of differentiation. Okay, this is a very important lesson as we're going to start to learn our derivative rules. So first, we know that derivatives can be useful to calculate the slope or gradient of the tangent line, as well as the instantaneous rate of change of a function. So we've used our derivatives already a bit. However, calculating derivatives using first principles can be tedious and time-consuming. As you can imagine, looking at some of our examples from section 14e, it takes a lot of steps to get to the answer. Fortunately, there are some rules that mathematicians came up with to help us simplify differentiation. And right here I have a short list of all of the rules. We're going to discuss each rule individually, and we'll use different notations for them as well. So the first rule is called the constant rule. If f is a constant function, meaning f always equals a certain number, like f of x equals 7 or f of x equals 10, then the derivative is always equal to 0. Okay? So for example, if f of x equals 7, then f prime of x equals 0. And that makes sense because if we have a constant function, that's just a horizontal line. And if this derivative represents the slope of the tangent, then the slope of a horizontal line is always going to be 0. The power rule is going to be very important. We're going to use this one quite a bit. If we have a function with x to the exponent n, then the derivative is always n times x to the exponent n minus 1. So imagine dropping this exponent in front as a factor and reducing the exponent by 1. So if f of x equals x to the 7, then the derivative would be 7x to the 6, right over here. If f of x is x to the 100, then the derivative would be 100x to the 99. Drop the 100, keep the x, reduce the exponent. We also have the constant multiple rule that says if we're multiplying our function by a constant value, remember that means a number, then the derivative is the constant times the derivative of the function. In other words, we can pull out that constant. It's almost like factoring out that constant and just taking the derivative of the function part. Okay, so if we have 8 times x cubed, then the derivative, we factor out that 8 and we take just the derivative of the x cubed part. The derivative of x cubed would be 3x squared, following the power rule. And if we multiply these two constant factors, we end up with 24x squared. Just a note, this little prime notation is me kind of showing you my thinking. I'm saying my first step is to pull out the 8, but I still need to take the derivative of this part. That's what this prime notation means. Another example, if I had something more complicated like 6 times x to the 8 thirds, I would start by pulling out that 6 and reminding myself I have to take the derivative of 8x to the 8 thirds. I'm going to keep that 6. I'm going to drop the 8 thirds, keep the x, and reduce 8 thirds by 1. So over here I'm subtracting 3 thirds from 8 thirds to get 5 thirds. And then I'm multiplying these constant factors. Here I can cancel out the 6 and the 3, leaving me with a 2 in the numerator, and I end up with 16 x to the 5 thirds. Or we could rewrite this in radical form as the third root of x to the exponent 5. Last, we have the sum and difference rule. If both f and g are differentiable, then so is f plus g. So if I'm adding two functions, I can take the derivatives individually and add them together. If I'm subtracting two functions, I can take their derivatives individually and subtract them. Okay, so this can be extended to a sum or difference of any number of functions. It works if I have 3 functions that are being added or subtracted. It works if I have 4 functions or 5 functions that are being added or subtracted. So for example, something a little more complex, I have 4 functions here that are being added and subtracted. I'm going to look at each one individually. I'm going to take the derivative of 6x to the 4, the derivative of 5x cubed, the derivative of 2x, and the derivative of 17. Using the power rule and the constant multiple rule, I get 24x cubed. I get 15x squared. I get 2. Now this is x to the 0. When I take the derivative of x, notice I drop the 1, multiply by the 2 to get 2, and I have x to the 0, which actually is 1. And the derivative of a constant is 0. So tidying it up a little bit, I get